You probably know the terms leaf, spine, and APIC, but the part that still trips up a lot of engineers is what ACI fabric is actually doing when traffic starts moving. In this lesson, you'll get a clear mental model for that. In this video, we'll make the architecture click fast. You'll see how the pieces fit together, what each part actually does, and how packets move across the ACI fabric. So by the end, you won't just recognize the diagram, you'll know exactly how the system works. If the intro video gave you the vocabulary, this is the next layer. It's where the design starts to make sense and you see why it exists in the first place. Traditional three-tier data centers were built for a time when a lot of traffic moved up and down the stack. Modern applications don't behave that way anymore. East-west traffic between servers, clusters, and services is often the dominant pattern. That's where the old model starts to feel awkward. You can end up with uneven paths, bottlenecks in aggregation layers, and a network that scales in chunks instead of clean way. ACI's fabric architecture is built around a more uniform idea. Any workload should be able to reach any other workload through a predictable fabric path. That gives you two big advantages at once. Traffic patterns become easier to reason about, and the network can grow by repeating the same design logic. And because ACI is policy driven, you're not just wiring ports together, you're defining intent, then letting the fabric enforce that intent consistently across the system. Let's build the fabric from the ground up. Start with the leaf layer because that's where endpoints and external connections enter the architecture. Then sits the spine layer, the fast switching core that links the leaves into one network. Notice what's missing. Leaves do not connect sideways to other leaves, and spines do not connect sideways to each other in the normal fabric topology. Instead, every leaf connects upward to every spine. That full mesh relationship across the two layers is what creates the fabric's consistent forwarding pattern. When one endpoint on a leaf needs to reach an endpoint on another leaf, the traffic goes into an ingress leaf, up to a spine, then back down to egress leaf. That means the network isn't hunting through a maze of unequal paths. The forwarding pattern stays intentionally regular. Low latency is achieved since traffic between leaves takes same number of hops. From a bandwidth perspective, it's just as important because the fabric scales horizontally. If you need more endpoint facing capacity, you add leaf switches and spine capacity for fabric transit. This is why spine leaf feels so different from legacy chassis thinking. You don't scale by making one gain center box more important. You scale by extending a repeatable system. Another way to say it is that the fabric is designed for symmetry. Any leaf should have equal fabric reachability through a spine layer. ACI spine leaf setup means a topology that makes pathing, scale, and performance are predictable. Keep that mental model in place because everything else in the fabric starts to make sense once you see that repeating leaf to leaf pattern. Now let's separate the two switch roles more precisely because a lot of confusion disappears once you stop treating leaves and spines like interchangeable boxes. Leaf switches are the fabric edge, servers, hypervisors, bare metal host, service devices, and external connections attached at the leaf layer. In ACI, the leaf is where the fabric first learns about endpoints as they appear, move, and send traffic. It's the edge where workloads attach and where policy is enforced as traffic enters or leaves that edge. The spine does a different job. It is not an endpoint access switch and it does not host endpoint facing policy decisions. It provides fast, consistent transport across the fabric, so any leaf can reach any other leaf predictably. You can think of the leaf as the place where the networks meet workloads and the spine as the place where the fabric stitches leaves together. That's why spines stay free of direct endpoint attachments. Mixing those responsibilities would break the clean architectural separation the fabric depends on. This separation also simplifies operations. When you're troubleshooting, you can quickly ask whether the issue is at the edge where the endpoint live or in the transit core that ties the fabric together. So, leaves are about attachment, locality, and edge decisions. Spines are about high-speed transit, reachability, and uniform fabric connectivity. Once you hold those roles clearly, packet flow gets easier to read on an ACI diagram. Now let's tackle one of the biggest ACI misunderstandings. APIC is central to the system, but it is not the box carrying you production packets across the fabric. APIC is the management and policy controller. It's where the fabric is defined, configured, monitored, and operated as a system. So when you create tenants, policies, application connectivity rules, or operational settings, APIC is the control point coordinating that intent. But once traffic is actually flowing between endpoints, the forwarding work happens in the fabric switches themselves. That means the data plane lives in the leaves and spines. Those are the devices making forwarding decisions and moving packets through the topology. A useful mental model is brain versus motion. APIC defines and programs intent. The switches handle forwarding in hardware across the fabric. That's why losing connectivity to an APIC is not the same as packets suddenly hairpinning through the controller. That forwarding path was never there in the first place. What APIC does is programs behavior, distributes policy state, and provides the operational interface, lets the fabric behave like one system instead of a pile of independent switches. What APIC does not do is sit in line in the packet path between endpoint A and endpoint B. So whenever you see APIC on an ACI diagram, read it as control policy and operations. When you see the leaves and spine, read them as live forwarding traffic. That split between management brain and forwarding fabric is fundamental. If you get that right, the rest of ACI becomes much easier to reason about. If APIC isn't forwarding traffic, but the fabric still knows where packet should go, how does it learn that? Start at the edge. An endpoint attaches to a leaf and starts sending traffic. That leaf learns the endpoint is locally attached. In simple terms, it knows this device is a workload that lives here. The key isn't just identity, it's identity plus location. The fabric needs to know what the endpoint is and which leaf currently owns reachability to it. If that endpoint moves, the fabric updates its views so traffic goes to the new attachment point, not the old one. That's why endpoint mobility matters in modern data centers. Workloads don't stay tied to one switch port forever. Conceptually, the fabric keeps a distributed endpoint location map, so ingress leaves know where to steer traffic next. That doesn't mean every switch blindly floods traffic everywhere just to find the destination. Instead, the architecture builds forwarding awareness that steers traffic towards the correct egress leaves. Endpoint connected leaves, the fabric learns their location, ensuring efficient forwarding. We will save the deeper object model and policy construction for the next lesson. For now, keep the architectural idea simple and solid. Now let's run an east-west packet through the fabric because this is where the topology becomes real. Imagine endpoint A is attached to leaf 1 and endpoint B is attached to leaf 2. The packet enters the fabric at leaf 1. That first switch is the ingress leaf because it's where the source endpoint hands traffic into ACI. Leaf 1 needs to determine where the destination lives. Based on fabric forwarding awareness, it identifies the correct egress leaf for endpoint B. Traffic moves up to the spine layer, linking leaf nodes. Packets are forwarded from the spine down to leaf 2, the egress leaf for the destination, and the packet is delivered to endpoint B. So the recurring mental picture is simple. The ingress leaf, spine transit and egress leaf, that's the pattern to burn into memory. Why is that efficient? Because the fabric isn't reinventing the path every time two workloads dock. It's following the uniform forwarding design. It's deterministic because every leaf has the same structural relationship to the spine layer, so the forwarding model stays consistent across the fabric. And it's scalable because adding more leaves extends the edge while the spine layer keeps providing the shared transit plane. Once you can narrate that packet walk without hesitation, ACI diagrams stop looking abstract and start looking operational. North-south traffic still follows the fabric's core logic, but now the packet is leaving the ACI world instead of heading to another internal endpoint. Now the traffic is crossing the edge. It's either entering from an outside network or leaving the fabric for a WAN, the internet, or another data center domain. Architecturally, that means the fabric needs a clear handoff point to the outside world. A simple way to picture it is this. At the fabric edge, leaf-based connectivity reaches out and ties ACI into external networks. So when traffic comes in from outside, it enters at the fabric edge, gets handled in the right leaf context, and then crosses the fabric toward the internal destination. When traffic leaves the data center, the path flips. It moves from the internal endpoint side toward the leaf layer that's providing external connectivity. Here's the key contrast. East-west traffic stays inside the fabric between internal endpoints. North-south traffic crosses the line between the fabric and external networks. That doesn't turn the spine layer into some legacy core doing random perimeter jobs. The architecture still keeps its fabric roles clean. Leaves stay at the edge where endpoints attach and external connectivity lives. Spines stay in the middle, moving traffic between leaves. So when you picture north-south traffic, see the same fabric in the middle, but now with arrows crossing in and out of the ACI boundary. That's the lens to keep in mind before you dive into the policy objects that handle external connectivity in detail. For this lesson, here's the key point. North-south traffic reaches the fabric through the edge, not through some hidden forwarding path. At this point, the architecture should feel a lot less mysterious. So now let's reset and clean up a few misconceptions that still trip engineers up. The first misconception is that APIC must sit in the forwarding path because it looks so central on the diagram. It doesn't. The second misconception is treating spines like legacy core switches with endpoint-facing responsibilities. That's the wrong mental model too. A third mistake is assuming the fabric is more complex just because it has more moving parts. In practice, the repeating topology often makes behavior easier to predict. That predictability is one reason the architecture scales well. The path logic stays consistent as you grow the environment. Another reason is role separation. Edge functions stay with leaves, transit stays with spines, and control stays with APIC. That separation makes troubleshooting cleaner too, because you're not guessing whether one oversized box is trying to be edge, core, and controller all at once. Operationally, ACI gives you a fabric that's easier to reason about once you think in repeatable roles and policy-driven behavior instead of box-by-box configuration. So the big shift is not just new terminology, it's a new way to picture the data center as a coordinated system. And that's why engineers who first see ACI as complex often later describe it as surprisingly logical once the architecture clicks. With the basic fabric layout complete, we are ready for the next level. Our next video focuses entirely on the hardware generations and platform naming conventions. We will also map out the core underlying protocols that truly make ACI what it is.